Distribution and route planning. This is an extremely important topic in logistics, and you'll see shortly why, because it can be costly to deliver small amounts of goods to a large number of destinations, right? And that's a lot of times what distribution has to do. Imagine Amazon delivering packages to customer homes. That can be a very expensive operation. This is sometimes called the last mile problem in logistics. So the last mile refers to the last leg in the delivery of a product from a supplier to a customer, and it is often the least efficient link in the supply chain. Why? Because most of the journey can be done with economies of scale, full truckloads or large LTL shipments, container loads, rail car loads. But at some point close to the customer, where the customer can be retail stores, the customer could be sites, construction sites where some product has to be delivered. Customer could be end customer homes. So customer does not just mean somebody sitting at their home at a residential address. Customer could be small warehouses. Customer could be retail shops. Customer could be construction sites, right? Depending on what you're delivering. So in any case, when you're delivering to multiple customers in an area, you can bring product into the area or close to it with economies of scale in large batches. And then you can have a cross dock or a warehouse, a local warehouse, where you do break bulk and you then deliver smaller quantities to individual customers. Bringing goods in large batches or full truckloads to a nearby location is going to be efficient and not very costly per unit. But then when you do break bulk and then you do delivery runs to regional customers, that part can be expensive, because you're delivering a small quantity to each customer and you're hitting many customers, so you're traveling a lot. This is sometimes referred to the hub and spoke model, where regional warehouses or distribution centers are hubs. And so if product comes in, is imported from outside the USA, it comes into the port in full container loads, it gets put on trucks go to these hubs, the regional distribution centers, and that's all very efficient and high volume, moving in large batches and with economies of scale, so that's efficient. But then from these hubs, you have to deliver to a lot of regional customers, and that can be inefficient. Similarly, if you have a factory producing something and you have one factory in the US, you can ship product efficiently to regional distribution centers, but then from there to end users or retail shops, that delivery may not be as efficient because you're delivering smaller than truckload quantities to each customer. You're doing maybe one pallet, maybe even less. And so we want to make this last mile part of the journey, this distribution to customers, as efficient as possible, because it is a major part of our transportation cost. Okay, so the hub to hub movement, like movement from port to distribution centers or factory to distribution centers or a national DC to regional DC, all of those movements are going to be relatively efficient using truckload type of shipments. But then the first mile or the last mile can be costly. What do we mean by first mile? In some logistics applications, you're collecting goods. Imagine recycling. Yeah, imagine waste collection. So to your home once a week, probably trucks come pick up waste. And that's very costly to pick up waste from every residential home or pick up recycling material from every residential home. A lot of electronic shops will have electronic recycling bins, and somebody has to go around pick all those electronics for recycling from all these shops. That's the first mile problem, collecting product from many different points. This could happen in farming. If you're in a country with many small farms and you need to collect corn or grain or whatever from these small farms, again, you have to go around, pick up produce from these small farms. And the opposite of that happens at the other end when you're distributing to customers as well. Okay, so the first mile collection problem and the last mile distribution problem, they're mathematically equivalent. Whether you go to a customer to deliver a small quantity or you go to a producer to pick up a small quantity, mathematically it's the same thing. You're driving there, you're spending some money, and you're doing some operation there, onloading or offloading or onloading, depending on pickup or delivery. And so our analysis and solving the problem would apply to both cases. It's just that in one case, you'll go out with a full truck and come back with an empty truck. And in the other case, you'll go out with an empty truck and come back with a full truck. That's the only difference. So what is distribution? What do we mean when we talk about distribution? Distribution refers to outbound transportation from a distribution center or warehouse, or could be a factory, or could be a port, to customer or retail locations. Selecting efficient routes is crucial to solving the distribution/last mile problem, because if you do not select efficient routes, you could end up spending more money than you need to on this part of this part of your logistics journey, or this part of your transportation. So the three types of route planning we're going to discuss. Well, the first one I'll just tell you, and you can just do it. It's called single source, single destination, and so you have to move stuff from one point to another. It's almost like a long haul or hub to hub movement. It's not really distribution, but sometimes you do have, you're just delivering to one customer from a warehouse or distribution center. And that's the easiest problem. You just find the shortest path in terms of distance or time, and you can use something like Google Maps to do it. And then you just go on the shortest path and do the delivery. So there's just one customer, one source, one place where the goods are coming from, and one place where the goods are going. Okay, so we're not going to talk much about that. That's straightforward. That's easy. Everybody can do it. Then we have line hauls, which is like relatively long distance trips between multiple sources and destinations. Imagine a company has multiple manufacturing plants, and they need to receive some raw materials at the manufacturing plant from multiple suppliers. So you may have 8 or 10 suppliers of raw material on one side, and then you may have 3 or 4 factories on the other side, and then which suppliers supply how much to which factory. You have to figure all that out to optimize your transportation costs. So we'll look at that a little bit, and then we will really solve it in a later lecture, but I'll show you what that looks like. And then the third one, which we're going to spend most of this lecture talking about, is delivery routing. Now, this is different from 1 and 2 because now you have one source point and multiple destination points. Okay, so this could be starting from an Amazon distribution center, going around delivering to different customers' home, different packages, coming back to Amazon distribution center. Or this could be starting from a Walmart DC in a big truck, going around to a different store and delivering some product, dropping off product at different Walmart stores, coming back to the Walmart distribution center. Okay. Or this could be a large national factory of shoes where you have, and this factory is directly going to supply wholesalers of shoes, and it's going to send a truck out because the wholesalers don't want a lot of one particular model. So when you make shoes in batches, each time you produce a batch of shoes of one particular model, you send out a truck and you deliver certain amounts to different wholesalers. So it could be anything like that, but the main thing is there's one source point where you're going to start the journey from. You're going to have multiple destinations. You're going to hit multiple destinations and come back to the source point. That's the important key. Okay. How is it different from 2? In 2, you're just doing line hauls between multiple sources and multiple destinations, where each truck just does one source and one destination. So you have multiple trucks moving, connecting different sources and destinations, but each truck is just doing one line haul, one movement from one source to one destination. How is it different from 1? 1 is just point to point, just one journey, and so it's different from 1 as well. So 3 is the most complicated one. And it is also the most costly per unit. If you divide your total transportation expense per unit, it's going to be very costly per unit per mile. How much it costs you, because your truck is a lot of times half empty, because you start with a full truck or a partial truck if the demand is not very high, and then you're delivering at multiple points. And then, after you've done first 2 drops, your truck is like half empty. You're driving around a half empty truck. By the end of the day, you're driving around a mostly empty truck. So that's why it's expensive, because you're not utilizing your transportation asset completely. and you're making many stops. Each stop is expensive because the truck driver is being paid and you're offloading the truck and so on. Okay, so the two versions of that. The first version is called the traveling salesman problem, and we'll look at that first. And then the second, more complicated version is the multiple vehicle routing problem. And the difference between the two is in the first version, you just need one truck because the amount you are sending out is small enough to fit on one truck. So one truck goes out, hits all the customers, comes back. So the only question left is in which order to hit the customers. Okay, because the customers are there and there's just one truck, the same truck has to go to each customer. In the second one, multiple vehicle routing problem, the quantity is so large it can't fit on one truck. Now you have to use multiple trucks. So now first you have to assign different customers to each truck. Okay, which customers will go to which truck, but then you also have to tell each truck which order to reach the customers in. So it's a more complicated problem. So let's start with number 2 here, line hauls with multiple sources and destinations. So that's called routing or transportation with multiple sources and destination. And if you have taken a course on linear optimization, these type of problems would have been called transportation problems, okay, because they're covered in any linear optimization course. Don't worry, we do cover linear optimization later in this course. So we will see how to set up this problem as a linear optimization problem in Excel and use the Excel solver to solve this type of problem. But that's not the order of business today. I just want you to see it so you know how this problem is different from the problem we're doing today, and then we'll solve this problem later on. This is an example transportation problem. You have some suppliers, they have some capacity constraints, so supply is less than equal to 400 for supplier A, supply less than equal to 700 for supplier B. And then you have demand points or manufacturing plants, and they have requirements. They have demand. Requirements equals demand, okay? And then you have these lines showing different transportation routes that you can take between each supplier and each plant. And then the number on the routes is a transportation rate in dollar per ton along that route. Okay. Obviously, if it's a longer route, the value will be higher because to move 1 ton along a longer route will cost more. And so the transportation rates would vary. You could define the rates as transportation rate as dollar per ton per mile, but just multiply by the miles in each route to get the value in dollars per ton. Because the way you're gonna solve this problem is you're gonna try to find what quantities flow in each arrow. So the amount of tons that flow on an arrow times the value of the arrow will give you the cost of that part of the transportation. Okay. Now you could have multiple options between two. So supplier A and plant 1, there's 2 arrows going and they could have different costs because one arrow could be truck, the other arrow could be intermodal rail. You could ship by rail and then use a truck to connect the last part from terminal to the plant, right? So you could have multiple arrows between 2 points as well with different costs. Okay. So this sort of problem is solved using traditional optimization methods, linear programming, the simplex method, things like that. And you can do this easily in Excel, and this will be taught in a later lecture how to do it. But this is a very different problem than the problem we're going to look at in this lecture, which is the delivery routing problem, which has 2 variations, the traveling salesman problem or the multi-vehicle routing problem. And we'll look at both of them. So let's look at the traveling salesman problem, also called TSP. This comes from this historical kind of problem because it's been found in books written like hundreds of years ago, where you have somebody who's going to travel, and this person is going to travel for some purpose. Maybe they're selling something, right? There's a trader, they bought some exotic goods in a faraway land, they brought them to their country or region, and now they're going to visit a lot of different towns and villages in the region to try to sell the product that they got. Okay. So the problem is that you have a list of destinations, just cities, towns, villages, and you know the distances between them. So you know if you're in town A, how much do you have to travel to go to town B from town A, and how much you have to travel to go to town C from town A. So you know all these distances because like you have a map, and the map is to some scale, and you can measure the distances on the map. Because if you have a good map and you know how to read the map, you would know this. Okay. So what is the shortest possible route that visits each destination exactly once and returns to the point of origin. So you're starting at your home base, maybe you're a trader, you're going to hit all these towns and villages exactly once trying to sell your goods, and you're going to come back to your home base. Okay, that's the problem. So what is the problem? Like, which order do you visit these towns and cities to come back, making sure you hit each one once, not twice, and then you also return. Okay, and you want this journey to be the shortest because you have other things to do in life and it costs you money to travel, and so you don't want to spend more time and money than you have to. There's still no algorithm which gives an optimal solution in a reasonable time when the number of destinations is large. Obviously, when the number of destinations is small, you can find the exact optimal solution by various methods like linear optimization. But the problem is that as the number of destination increases, the problem complexity increases non-linearly, so that for large number of destinations, the problem gets really hard to solve in a small amount of time. It takes too long to solve it. Okay, so if you can't find the optimal solution, what you can do is you can do a heuristic technique. Heuristic technique means it's an approximation. You can't find the exact optimal, but you can be approximately optimal in much, much less time. So maybe it takes you years running on a computer to find the optimal solution, but an approximately optimal solution, which is close to the optimal, maybe you can find that in 5 minutes or 10 minutes. So obviously you would go for the approximately optimal solution because you can't wait multiple years to do this trip or to do this distribution trip, right? So this is typically encountered in logistics when you are trying to figure out, you have one truck, it's got to deliver or pick up from multiple points, what order to visit those points in. That's where you encounter this traveling salesman problem. So we're going to look at a couple of examples of, some interesting examples of this problem. And then we're going to look at how we can solve it. So some heuristics, okay? Because as I mentioned, for large number of destinations, there's no algorithm which gives you the best solution in a good amount of time, in a small amount of time. It takes too long to solve it for large number of routes. So let's try to solve this problem for a tourist. We have a tourist, and this tourist wants to make at least one stop in all 48 states in the contiguous United States, because this tourist wants to visit the US. It could be one of you who wants to go see the US. And in each state, you want to visit some national historic site or natural landmarks or national parks or some national monument. Something big that state is known for, you want to visit that. And you're going to do it as a road trip. You're going to drive your car around. So once you graduate from this degree, it might be something worthwhile considering. Go on a road trip, visit, a lot of natural monuments and historic sites in the US. So obviously, we don't want to just waste our time driving around needlessly. So we're going to find the shortest trip that's going to make these 48 stops and come back to wherever we started from. So you have some starting point. We leave our home, and when we have to come back to home at the end. Okay, so now let's look at the complexity or the size of this problem. Okay, now we are going to visit 50 landmarks in 48 states. Why 50? Because 50 is a nice round number to talk about. You could pick 48 landmarks to visit in 48 states, but just as an example, we're going to visit 50 landmarks in 48 states. The reason we're limiting to 48 states is we want to complete the journey on a car. We don't want to have to fly or take a boat. Okay. If you have to visit 50 stops in the contiguous United States, continuous land mass of the United States, there are 50 factorial possibilities, different orderings in which you can visit these points. So if you go to point 1, then point 10, then point 15, then point 34, so on and so on, that's like one ordering. You can get 50 factorial possible orderings of the 50 landmarks. What is a factorial? A factorial means a number multiplied by a number which is 1 less, multiplied by a number which is 2 less, on and on till you hit 1. So 5 factorial is 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. 3 factorial is 3 multiplied by 2 multiplied by 1. 1 factorial is just 1. And 10 factorial will be 10 multiplied by 9 multiplied by 8 multiplied by 7, on and on till you multiply by 1. Okay, that's what a factorial is. So 50 factorial gives you 3 times 10 to the 64 possible roots. 10 to the 64 is 64 zeros. So you take 3 and you add 64 zeros at the end. That's the number of possible roots you have to evaluate the distance for, and then pick the one with the shortest distance. So imagine if you have a computer and you tell it, okay, add up the distances for this 3 followed by 64 zeros, this many roots, to find the total distance of each root, then sort them or find the root with the smallest distance, give me the root with the smallest distance. That computer is going to be working for years and years to solve this problem. Okay, so some estimates, because nobody has run the whole problem and seen the exact time, but some estimates are, if you started computing this problem on your home computer, your laptop right now, you would find the optimal root in about 9.64 times 10 to the 54 years. Okay. So imagine with just 50, it gets so impossible to find the optimal route. This is also why Google Maps limits you to very few waypoints when you do routing with Google Maps. So you tell Google Maps you want to go from home to some place and you have these, 8 or 9 or 10 points you want to stop on the way. It will not let you add usually more than 10. At least that's the limit I've encountered, because when you add more than that, it takes too long to find the optimal route because there's just too many possibilities to evaluate. Okay. So we can't find the exact optimal solution. So we'll do a heuristic solution. We'll find an approximately optimal solution. Okay. So all of the heuristic methods that are going to work with this, they need the same type of input. The input they need is all possible distances between a pair of 2 points. Okay. So what is the distance from point 1 to point 2, point 1 to point 10, point 1 to point 49? Similarly, what's the distance between point 30 and point 35, point 30 and point 7, point 30 and point 42? Any 2 pair of points, what's the distance between them? Okay. And so what you do is you list all the 50 landmarks as 50 rows in Excel, and then you list the 50 again as 50 columns, and that gives you a matrix, like a table. Matrix is just a table of values, which is 50 rows by 50 columns or 2,500 entries. And then once you fill it up with all the distances, you can give this matrix to any heuristic algorithm to find the approximately best route. Okay. Now you might say, oh, that's going to take me forever to build that matrix. Well, you don't do it by hand, because those 50 landmarks, you can do it 2 ways. These 50 landmarks will have longitude and latitude coordinates. So you can use the coordinates, plug them into a formula to find the distance in miles between any 2 coordinates. Okay, so longitude, latitude coordinates, you can find the distance between 2 points where you know the coordinates of both points using a formula. That will be a straight line distance. A road may not go straight line. Usually a road will not go straight line. So what sometimes we do is we multiply that distance by a factor. So okay, the straight line distance between 2 points is 100 miles on average in the US. Okay, the distance by roads between 2 points is about 30-ish% more than the straight line distance. So you multiply the distance by 1.3. So you say, okay, the straight line distance based on the coordinates is 100 miles, but I'm going to go on roads. Roads are going to curve, move here and there, right? So it's going to take me 30% longer to get there. So my actual distance traveling by road will be 1.3 times 100 or 130 miles. So you can estimate the distance between any 2 pair of points if you know the coordinates of the points. That's one way you can build this matrix by just using a formula. A second way is you can write a small program, and with AI, it's not that difficult to write a program where you call an API service. Like a Google has a server where if you have paid some money, or it might even be free for up to a certain limit, where you can pass it coordinates of points, and Google will run their Google Maps software and find the distance on the exact roads and the time it will take you to travel between those points and return you that value. And there are other API services like that where you can pay a little bit of money and give it pairs of points, and it'll give you the actual road distance using maps between those points. You can either use a formula with a 30% estimate that the straight line distance plus 30% of that will give you the road distance, or you can write a program to call an API service, a server, which will do this calculation using maps for you and give you the exact distance using road maps. So that's not too hard to build this matrix. So once you've built the matrix, now you can use those algorithms. So this is one solution that somebody coded up, and a link to the article that explains their solution is in the notes of the slides. So they use what's called a genetic algorithm. Okay, all these heuristic algorithms have this common theme. What they do is they start with some feasible solution, even if it's a bad solution. They just find one solution, or 3 or 4 or 10 feasible solutions. Usually they find more than one. So you find a few feasible solutions, and then you modify these feasible solutions to make them better. Okay. Sometimes you modify them by taking like multiple feasible solutions and saying, okay, in this feasible solution, this eastern coast of the US is done really well. So I'm going to take that part here, and I'm going to take the west coast part from a different solution, and I'm going to combine these two solutions into a new solution. That's something that genetic algorithms do. They mimic this evolutionary behavior where genes can combine in different ways to give you better performing systems. So they say, okay, we're going to look at these solutions. There's a pool of organisms in a way, and we're going to take different parts of different solutions to construct new solutions. And we're going to try to make sure these new solutions are a little bit better than the old solutions. So once you do that, once you make a little bit of improvement in your solutions and you get new solutions, then you repeat this process again and again at each step, trying to improve it a little bit until it gets really hard to find improvements. And then you say, okay, these are the 5 or 10 solutions I'm left with, and you take the best of those 5 or 10 solutions you're left with. So that's the idea behind genetic algorithms. Most heuristic algorithms work in something similar. The thing that differentiates them is how do you go from a feasible solution or a set of feasible solutions to a slightly better solution or a set of slightly better solutions. So you could do some swapping where you just change the order of 2 things between different solutions to reduce the distance a little bit, or you could do things like that. So I will give you a link to a YouTube video that will show you a bunch of these heuristic algorithms in action with a visualization showing you how the routes are changing. And you'll see this happen. You'll see they start off with like a route, like just a randomly picked route, and then they'll slowly improve it to get to a better route. Okay. So in less than a minute, genetic algorithm reached a very good solution, okay, which hits these 50 points you can see on the map. And the full traveling distance start to finish along this route is 13,699 miles. Okay. There is an extra stop in Cleveland because otherwise the route would go through Canada. When you go from Vermont to Michigan, the shortest distance goes through Canada, and we wanted the journey to not require any border crossing or any visa issues type of thing, so that you can stay within the US and do this journey. So an extra stop was put in Cleveland to force this route from Vermont right here at this point, not to go through Toronto and Canada and Ontario, but to go here to Cleveland and then to Detroit. Okay. So the route we picked, the closest city or the closest town for each monument was picked. And then you did this routing so you can visit all those monuments. Assuming no traffic, this road trip will take about 224 hours or 19 12-hour driving days. Obviously, if you're driving 12 hours in a day, you're not doing much sightseeing. So if you want to stop for sightseeing, one day at each site or so on, probably take you about 2 months to complete this whole thing. So if you want to go on a 2-month road trip, here's a great idea for you. You'll learn a lot about, your country. And if you follow the link in the notes of the slides, hopefully if the webpage is still up, you can get the exact details and a link to this actual Google map where you can see the exact places you're stopping and so on. The same thing was done for Europe. So here's an article on 50 places you must visit in Europe. And so the same algorithm, the genetic algorithm or the heuristic algorithm, was fed those 50 sites in Europe. And so you can visit a lot and then see a lot of Europe doing this trip. This European road trip is 16,287 miles. Okay. And you'll notice that because you're going to United Kingdom, you're going to have to put your car on a ferry and cross over this over water. Okay. So in some cases in the European trip, you're going to have your car go on a ferry and then the ferry cross over water. There's just no way to just never cross water. Okay. So yes, that's 27 12-hour driving days. Obviously you stop. You may not drive 12 hours every day, and you're going to make stops in between. So it might take you 2 to 3 months to do this trip. 45 stops are covered, not all 50 given in this article, 50 must visit places in Europe, because some couldn't be reached by car. So, you know, these you will still end up seeing a lot of Europe if you do this trip. So this is these two examples show you we are solving the traveling salesman problem. Okay. Now, usually for logistics, you're not going to be traveling over the whole of the US or the whole of Europe with just one truck delivering goods. You're usually going to be traveling over a much smaller region. Maybe your truck just delivers to places in Michigan or Michigan and Ohio, right? And so, but the idea is the same. You'll have multiple points in Michigan or Ohio. You'll do this trip hitting each point once and coming back. Okay, so the math is the same. I just picked these examples because they might be of interest for you, and they might show you, you know, how this heuristic does this cool thing and can optimizes your driving distance for you. So let's look at how to solve these sorts of problems. Okay. For the genetic algorithm stuff, we will use an Excel file called a vehicle routing model in Excel that uses a code written in Excel, in Visual Basic in Excel, and you'll be solving a problem on it. And I'll upload a separate video explaining how to use that Excel tool to do this sort of genetic genetic algorithm thing. Okay, so I'm not going to show you how to do it manually because it's very computationally involved. You can't do it by hand, but I will show you how to do it in Excel using an Excel sheet specially built for it with code behind it in a separate video on how to do this genetic algorithm to solve this problem. Okay, so that you can see in a separate video. I'm going to show you some simpler ways, heuristics to solve this problem. And the first one we're going to look at is what's called the nearest neighbor. Nearest neighbor is from a class of heuristics called the greedy heuristics or greedy algorithms. And the idea behind all these heuristics is that you are very short-term focused, and wherever you are, you just pick the next best thing. Okay? So wherever your starting point is, you're going to go to whichever point is closest to you, because at every decision-making point, you're going to decide on what's best for you in the short term. So for now, the shortest distance for me is to this point. So, you know, if I have 20 customers to visit, I find what customer is nearest to me to my starting point, and I go to that customer first. When I'm at that customer, I say, okay, now that I'm here, of the remaining customers I've not visited, which customer is the closest to me from this first customer that I visited? And then you go to that customer as your second customer. So you just try to make each jump to be the smallest one. And you might say, oh, well, that will give you the shortest route, but no, it does not. Okay, the shortest route, it's not good. It may in some cases, but it's not guaranteed to give you the shortest route overall. I'm going to take you through a couple of examples of this, and a third example is linked in this YouTube video. So this video takes you through an additional example. You don't have to watch it because I'm going to show you two examples in the lecture, in the slides. But if you were interested or want to see another example of how this nearest neighbor algorithm works, you can watch this video on your own time. So here is the algorithm listed, a bunch of steps you can follow. Okay, start on an arbitrary point and mark this point as visited. Okay. Now this is the step number one is usually not required in logistics because your starting point is known. You're starting from a distribution center or warehouse or factory or a port, right? Or a railway terminal or whatever your starting point is where your goods are. So the step one only applies if you are doing the classic TSP, traveling salesman, and you have the option that you can start anywhere. This is the classic TSP, not thinking about delivery of goods from a distribution center, so it's an arbitrary point. But for logistics, okay, usually we know our starting point. So you start with there. You don't start at a random point. Okay, you start with your starting point in logistics. So starting point is known in logistics. Okay, why? Because that's going to be where your inventory of goods is. Where is your inventory? Okay, that is where your inventory is. You can't just start at a point where you don't have your goods. You have to deliver your goods. Or you have to pick up goods. So in that case, you're going to start where your truck rests, your truck's resting point is, right? the truck terminal or whatever. So, or the truck just finished a delivery round, it's going to start at your DC because the truck just came back from something else, then it's going to start a pickup route or whatever. So with your inventory, and it's going to be either a DC, factory, port, rail terminal, something like that. So that's known. Find out the shortest edge connecting, which is the shortest distance, connecting the current point to an unvisited point B, V. We talked about that matrix. All these heuristics, you have a matrix of distances between every two possible pair of points. So whenever you're at a particular point, you look at that row of the matrix. Okay, I can go from this point to any other point. So what are my distances? And you pick the shortest one. Okay. And you only look at unvisited points. Okay. Whenever you are picking out where to go, you don't want to repeat a point. You want to go to someplace you've already been. Okay. Move to the unvisited point that you picked in step 2. Mark that point as visited so you don't consider it again. If there are unvisited points remaining, then go back to step 2 to find out which point to visit next. Otherwise, if you visited everything, there's nothing left in the unvisited list of points V, then you just return to the starting point at the very end. Okay. So let's actually do an example. Okay. So we're going to start at this point A. This is my A. Okay, that's my starting point. And I have to visit all the other points B, C, D, E, and come back to A. And the distances are listed along the lines. So just look at my options from A. I can go this way. That's one option. I can go this way. I can go this way. I can go this way. I have 4 options from A. I can visit B, C, D, or E. If I look at the distances, this distance is 200 miles. This distance is 500 miles. This is 205 miles. This is my shortest distance. So I will go along this route from A and jump to D. So this is my first point. I started here. I jump to my second point, which is D. Now D has been visited, so I'm not going to consider D again. From D, and I've already come from A, so A is done. So I'm not going to consider this route again. I'm just going to look at this one. That's an option. That's an option. And that's an option. I have 3 options now. Because I can't go back to A. It doesn't make sense to go back to A. I have not finished my visiting every point. So between these 302, 360, 320, obviously 302 is the smallest. So I go here and I end up as E as my third point. I end up here. Okay. From E, I can't go back to D. I've already visited, I just come from D. I can't go to A because A has already been visited. So A and D were both visited. I can't go here. So I have only 2 options left. This, which is 340 miles, or this way, which is 165 miles. So obviously I pick the shortest distance. I go here to 165 miles and I go to C, and that's going to be my 4th point that I visit. I've come for E, so I don't consider this. I've already visited D, so I cannot consider this. A, I started from A. I've already visited A, so I can't consider A. So I have only one option left, B. So no matter what miles I have to go to B. There's only one option left. So I visit B at the very end as my 5th point. And now every point has been visited. There's no unvisited points left. So I just have to go back to A over this 500-mile route because all points have been visited. So I just return to the starting point. So here's my order. A is 1, D is 2, E is 3, C is 4, B is 5, and then just come back to A. So that's going to be a route. A, D, E, C, B, A. That's going to be a route. Total distance of this route is 185 plus 302 plus 165 plus 305 plus 500, or 1457 units of distance. Okay. So there's, we just run nearest neighbor and we found a solution. Okay. Now you'll soon see that this solution is not optimal because I'm going to do this nearest neighbor again from a different starting point. So let's say I start at B as 1. That's my first starting point. You look at all the 4 places you can go to from B and you find the 305. This one is the shortest route. 500, 340, 360, 305 is the shortest. So you go to C. Okay. Then you'll see that from C, you'll go here. 165 is the shortest here. Then from here, you'll go to A. Then from A, you'll go to D. And from D, you'll come back. Okay. So you should verify following these steps that this is the route you get. B, C, E, A, D, B, and then back to B. Okay. Total distance of this route is 1220. much shorter than the previous route. So we know nearest neighbor does not give us the optimal route because this was nearest neighbor starting at A and it gave us a much longer route, and this is nearest neighbor starting at B. Nearest neighbor beat itself and gave us 1220. Now you might say, well, this is not fair because you're starting at point B and let's say our DC is at point A. We don't have an option of starting at B. But don't give up just yet. Okay. All of these routes, B to C, to E, to A, to D, to B, make a circle. So I found this circle starting at B, but I don't have to start at B. I can do this same circle I've identified and start at A. So how would that be? So look, B to C, to E, to A, to D, to B. That was the route that nearest neighbor gave me, right? I can just start at A. Let me change the color of the pen. I can start at A and go this way and go around and come back. That'll give me A to D to B. B to B is the same. I don't have to do it at B to B. B, I'm already at B. So I go to C. So after B, wrap around and you skip this B because you've already been at B, and you just go to C. And then you go to E, and then I come back to A. Now you can verify, okay, that A to D is 185 miles. D to B is 360. B to C is 305. C to E is 165 and E to A is 205. This distance, okay, is exactly 1220. So even though I'm starting at A now, because I'm doing a full circle, so it doesn't matter where I start, I'm going to get 1220 miles with this route. So I can any circular route that nearest neighbor finds, I can always adjust the starting point. So one slight improvement that people do, because nearest neighbor is really fast run, computers can run this in like a microsecond or something. Like before you can blink your eye, computer will be done running this algorithm. It's so simple and straightforward. So what you can tell the computer is, find nearest neighbor route starting at A. Okay. Find the NN route starting at A. Then find the nearest neighbor route starting at B. Then find the nearest neighbor route starting at C, and so on. Then D, then E. So you find 5 nearest neighbor routes and you pick the shortest one. You pick the shortest one. And then you can use this property of circles to convert that route to starting at whatever point you want to start at. So notice that for the nearest neighbor algorithm, all these heuristics, you always give it your distribution center as well. So A was our DC. So we have to just give A as a point. You just don't give it 4 points of your customers and say find the route between those customers. You always give it your DC as one of the points as well, because you want to return to your DC. And so, when you run these heuristic algorithms, one of the points is always your distribution center, your starting point, and the other points are your customers. Don't just give it a list of customers only. Okay, include your DC there. So in any case, because you are moving in circles, you can always adjust the starting point, just rotate the circle and still keep the same distance on these routes. And so one modification of nearest neighbor is just run nearest neighbor algorithm from each point as a starting point. And whatever gives you the shortest route, then just modify it because it's a circle, just modify it, start with your starting at your starting point, and you'll be able to get the same distance and do it from your starting point. Okay. So the route can vary depending on the starting point. We just saw that. Because the algorithm is efficient, often it is run starting from every possible starting point. So if you start at A, you get this route with this distance. You start at B, you get this route with this distance. Then you can start with C, you'll get some route with C and ending at C, and you'll get some distance, right? And then because we prefer the shorter route, you take the shortest route, and then you can just rotate the points to get it starting at A. Okay, but where says A, all routes are circles, any route can be rotated to start at any starting point. So you can rotate this route by starting at A, doing ADB first. So you do ADB, and then you do BCE, and then you BCEA. So then you do the this part of the journey, BCEA, and then that's this part, BCEA. Okay, so you can move to any starting point. The distance would remain 1220 when you rotate the route. So that's how you can use nearest neighbor, and this is very practical. And at least you have one way to solve this complicated problem even by hand if you wanted to. Okay, and this is not a small skill. I had a student who got an internship, particularly because he knew all about routing from my course, and that was a reasonably large company, but they had no software to do this routing for them. They were putting thumbtacks on a map and doing the routing manually. And that was his internship. He would help make routes for them, and they were collecting stuff for recycling. And they were a recycler, electronics recycler, and they would collect electronics and then recycle them. Okay. And this is important because there's a lot of small and medium-sized companies out there who don't have complex industry strength professional software to do routing for them. And they can, and so all the techniques you learn in this lecture, you can use with that. We're going to learn relatively complicated heuristics in this lecture to be practically relevant. You can actually, in practice, in real life, solve this problem for companies who don't have a software to do it for them. Okay. So one thing you learn is to do this nearest neighbor. You could do it by hand, and you could do it from every starting point and pick the one with the shortest distance. And so you have one toolkit one tool in your toolkit to hit the problem with. And then the second tool is this genetic algorithm one, which I will teach you in another lecture, the Excel tool to use. You could use that as well. So you could use that Excel file with the genetic algorithm to do it for you. And you could do nearest neighbor. So two tools we have covered. Well, one we will cover in detail later, but you know the idea. And then the second tool, and we're going to do more of them. So how good is nearest neighbor? So people have done simulation studies, and they just randomly plop endpoints on a plane and run nearest neighbor to find the route, and then they find the optimal route for those endpoints and see what's the comparison. Optimal route finding obviously takes much longer, but they want to find the performance of nearest neighbor, so they have to compare to the optimal route. And on average, it yields a path which is 25% longer than the shortest possible path. Now that's not very good, but it's also not bad. Okay, because 25% longer means you can cut down 25% on your transportation expense if you were to find the optimal route. Well, optimal could be really hard to find. So if you use other better heuristics, you may cut down maybe 20%, 15% transportation expense, right? But you're getting in the ballpark, right? Nearest neighbor gets you in the ballpark because there are much worse routes out there that, we skipped over to get to this route. One way to look at if nearest neighbor gave you a good route or not is to look at the last few stages of the tour. Are they comparable in length? Then the tour is probably reasonable, or the route is reasonable. But if the last few stages have much longer length, then it's likely that much better tours exist. Look at this example. Okay, the last leg B to A is 500 miles. It's a lot longer than the other legs. They're about 200 on average, 200 to 300, or 150, 160 to 300. This is an outlier, and the outlier was the last leg of the journey. So we know this route is not the best. Most likely better routes exist. And here we found a better route. And in this route, the last leg is 360 miles. Okay. Which is less than 500, not the shortest, so maybe better routes exist, but not as bad as before. So that's one way you can get a sense of whether nearest neighbor gave you a good solution or not. Sometimes it can be a lot worse than 25% off. That's on average, right? It can be less than 25% off. It can be more than 25% off. Okay, and so that is, it's not terrible, but it's not the best heuristic out there. Here's a YouTube video showing you different TSP heuristics. I'm just going to play it a little bit. And I highly recommend you watch this video because it's going to show you the swap heuristic, where you swap parts of the part of the routes. You swap the order in which you visit certain points to get to better routes. And you'll see how you start with a really long route and you get to a much better route. Okay. So this is the greedy algorithm, which is nearest neighbor. Greedy is nearest neighbor. You're doing nearest neighbor now. Okay. So notice this route is really terrible because you're kind of crossing over each other. Usually good routes don't have this crisscrossing like this X type in them. Okay. So this will produce a suboptimal route usually, and we already know that it's only 25, on average it's 25% of the optimal. It's 25% longer than the optimal route. These cross over itself, simple fix, you can do a swap. So you swap two edges to make a new route, and this is a better route. You can see the distance in the bottom. So 8.6 something became 8.5 you save over 100 kilometers. So you start with an initial solution in this heuristic, which is the 2-opt swap. So this initial solution is terrible. See how much crisscross is happening? It's a terrible solution. Now you start swapping the order in which you visit routes and see how the distance is dropping. You're getting better and better each time you get a better route. You're still visiting all the points, just swapping the order in which you visit them. As you do the swapping, you can see the crisscross reduces and you get better and better routes. So you're down to like less than half of the original length. So this, you went from like 40,000 to 16,000 kilometers. There are still better routes, but the 2-opt swapped got stuck. So that is called a local minimum. Local minimum is when you are doing this heuristic algorithm, you're swapping the order in which you visit routes, and then this is different than genetic algorithms. In genetic algorithms, you don't do swaps. What you do is you pick sections of the routes and you connect them in different ways. But this is 2-opt swap is not too different. It's doing the same thing, but at smaller scales than a genetic algorithm. But you can see that you can get stuck in a local optimal where you have a good answer, but it's not the best answer. So another way is to do what's called simulated annealing and other ways. So it's going to show you simulated annealing next. So we were here, we found the initial route, okay, and now it's going to walk you through how to do better than that. So some greedy selections early on may take a second local optimal. So now we're going to try to avoid that. We accept worse solutions early on. We don't always go for the local optimal. And then slowly as time goes on, then we stop accepting worse routes. And this allows suboptimal solutions to exist initially because you could have a suboptimal solution initially that becomes a much better solution in the end. Okay, so this is what it's showing you. And obviously you can't do this thing. I mean, you can do it by hand. It takes you a long time. This is often done with computer algorithms. And we will learn a use of an Excel sheet with one such algorithm built into it, a genetic algorithm built into it, when we do that. The VRP Excel solver. Okay, so you can watch this video in your own time. But that gives you some overview of how these heuristic algorithms work. Now, you can also do TSP by hand by plotting your points on a map. Just have a map on your table, draw X's on it, the points you want to visit, and just kind of draw a teardrop type of pattern to visit them. Cognitive psychology researchers have observed that humans are able to produce good quality solutions quickly when the number of destinations is not very large. They can just eyeball it. They just look at the map and it's connected with the hand and they do a good job, right? The amazingness of the human mind. Good eyeballed human solutions often follow a teardrop or flower petal pattern with minimum crossing of paths. So you can see these are both kind of like teardrop flower petal type patterns, but A is not the best one because you cross over yourself a lot. But this B is a little bit better route than A. Okay, so just draw like a teardrop type of pattern going around like in a circle-ish type of oval type of shape, hitting all the points. I mean, it's not going to be oval. You're not going to go in a curve. You're going to go along, from the depot to the point in like a straight line, or as close to a straight line as possible by the roads. But the order in which you select them gives you this teardrop type of pattern. So you don't go from east to west and west to east and back west and crisscross all over the place. You're just going to go in this teardrop type of pattern. Yeah. So that was the traveling salesman problem. You can eyeball the solution. You can do nearest neighbor, which is the greedy algorithm. You can do two-opt swap or genetic algorithm heuristics that are built into a computer software. And I will give you an example with an Excel file in an addendum in a second part of this lecture, where I'll talk about how to do it in Excel. Okay, so you have various ways to attack the traveling salesman problem. Now we're going to do the more complicated version of that, which is the multi-vehicle routing problem, where your quantity is so large that it cannot be put on one vehicle, so you have multiple vehicles to do this routing. Okay, so the multi-vehicle routing problem is basically the traveling salesman problem, but now we need to use multiple vehicles. So there could be restrictions placed, like a mixture of vehicles with different capacities. You may have time windows on the stops that you have to deliver in a certain time window. A lot of delivery services, if you buy furniture or appliances, they'll give you a 4-hour window in which they'll deliver. Customers like it because then they have to be home for that point. But it does, the more restrictions you put, the more expensive your routes can be, because some of the best solutions may not be possible because of these restrictions. So let's say the optimal route is one way, but in that optimal route, you make your optimal route, and then you give if you want to if you allow customers to pick their time windows, then it can really destroy your optimality, because you have to be at a certain customer at a certain time, and then that affects the order in which you can visit the customers. So often the companies will not let you pick a time window, but they'll notify you of a time window when they'll be there, because once they find the optimal route or the heuristic solution, which is approximately optimal, then they can tell you approximately when they'll be there. And then they can give you a time window. But they won't let you pick a time window, because that can be problematic. That can give them very expensive routes. And the time windows on the stops, the restriction is having the customer pick the time window. The customer says, I prefer this time window, I don't want this one. If the customer is not picking the time windows, you're just informing them of the time windows, then that's not a restriction, because you can just find your best route and then just find the time windows and tell the customers. Okay, so when we say a restriction is placed on the time windows, that means it's like a customer preference, and that is not just simple informing after the fact, after you've made your route. If you can have pickups combined with deliveries, like some customers, you may pick up the old appliance when you deliver the new one, for example. And then it's usually a restriction on total travel time for a vehicle. So in the US, Department of Transportation guidelines, a truck driver can't drive a truck more than 11 hours in a day. And so then, you have, and cannot work for more than 14 hours in a day. And so you have restrictions like that on the time, which could limit how many customers you can reach, depending on the distances between them. So we're going to do some practical guidelines for good routing with multiple vehicle problems that you can use to build your own routes on a map. Just plot your customers on a map and build your own routes, okay? The first is that you want to assign customers which are close to each other to the same truck. So look at, which means you need to group customers together by geographic location. Okay, so if you cluster customers together, then you can assign a cluster, for example, to one truck. Now, this is an example where it's the same set of customers in both pictures with A and B. But in picture A, the user has drawn two vertically elongated ovals to cluster the stops. And that is not good. Why? Because within a cluster, points should not be far apart if you want to get good solutions. And if you look at V clustering, you can see that some points within the cluster are really far apart. Okay, there's a big distance between certain points. A better option to cluster the same group of customers is shown in diagram B, where the distances between customers are small. When you hit the first customer, going to second customer is not very far, going to third customer is not very far. Same for the top cluster, where once you hit customer 1, customer 2, 3, 4, all the rest are kind of in the same area. You're not traveling too far to get to them. Okay? So these guidelines have been developed by people looking at running a lot of heuristic algorithms, looking at the good solutions, looking at the bad solutions, and trying to identify what separates the good solutions from the poor solutions. Okay, so these are like heuristic rules. They work well in most situations, but you can't say that they're absolutely will give you the optimal answer every time. But these are like rules of the thumb you should keep in mind. Okay. So the first one is clustering. Make sure that the distances between points that belong to the same cluster are not large. Then if you're doing stops on different days, then you want to schedule the stops based on their geographic location. So look at option A, where you have some Thursday stops, T is for Thursday, okay, that are very near the Friday stops, and you have a Friday stops like right next to Thursday stops. So you are overlapping in both days. So on Thursday, you're going to go to a region where you're going to skip a customer just because they're scheduled for Friday. And on Friday, you're going to go to a region where you're going to skip a nearby customer because they were scheduled on Thursday. So that's not good. So you want to assign customers to the same day of the week for a delivery, which are close to each other, and there's no overlap in the journeys. You can look at option B, the dotted line, there's no overlap. Okay, whereas in option A, there is an overlap. Overlap means you're visiting the same region twice. Lack of overlap means you're not revisiting the same region twice. So we don't want overlap. And so you may have to work with sales to move some customers' delivery day, or don't assign them delivery days before you do the clustering. Do the clustering and then tell the customers the delivery day, so that you can get better clustering. Okay. So if you're, let's say, Macy's and customers buy furniture and you're going to schedule their deliveries, you do your clustering before you call the customers and you offer them a delivery day. Okay. And then you tell them, okay, you're next, I'm going to be in your area on a Thursday, so please, this is a delivery day for you. Obviously, sometimes, based on your customer service policy, you can't do this all the time. Some customers are allowed to pick a delivery day, and then this may not be possible if they pick a different day, but we try to do this as much as possible. Again, it's the same idea as here. This first point was don't have too much distance between points that belong to the same cluster. And here the idea is don't have overlapping cluster. Don't visit the same region in multiple clusters, because multiple clusters get assigned either to different trucks or different days of the week. And so you don't want to visit the same geographic area by two different trucks, and you don't want to visit the same geographic area on 2 different days of the week if you're doing like a weekly run for each area. Okay. And so non-overlapping clusters and not a lot of distance between points in the same clusters. The third rule is to build routes beginning with the farthest stop from the depot. So once you have this clustering done and you're going to build a route for a cluster, which is one truck is going to hit that one cluster, you want to hit the furthest point from the depot, and try to pick 2 spots close to each other if they are kind of far from the depot and starts with them. Okay. The stop sequence on a route should form a teardrop pattern. Okay. Now, obviously, if customer gets to pick the time windows, this teardrop pattern will get messed up and you might have to crisscross a little bit. But you want to avoid that as much as possible. If you can live with not having the customers pick the delivery time and you just notify the customer ahead of time of the delivery time, that's fine. That's much better. Okay. So notice that in every diagram I've shown you, I get a teardrop fashion. Teardrop type of pattern. Okay, here you got a small teardrop, then you like a bigger teardrop on top, but still teardrop type of pattern. No lines crisscrossing, no clusters overlapping. The most efficient routes are built using the largest vehicles available first. Pickups should be mixed into delivery routes rather than assigned to the end of the routes. Okay, so don't do all deliveries and then do all pickups. Just look at the points you have to visit. If a pickup is right next to a delivery point, just after delivery do that pickup. Don't have to go to some other delivery and then come back to the same region again. Again, this is to avoid crisscrossing and visiting the same region twice. A spot that is greatly removed from a route cluster is a good candidate for an alternative means of delivery. So consider if you have some outlier points that are just far from everything and there's nothing, no other deliveries close to them. Consider if you can just outsource that delivery to a third-party delivery service and pay them, or you can send the delivery by parcel like UPS or something, because that might end up being cheaper than sending your truck, just one truck to do one delivery to that point and just coming back. And just sending, paying for the whole truck, the driver, and all of that just to do that one point, because you're not going to be able to combine that with other deliveries efficiently. And avoid narrow stop time window restrictions that are chosen by the customer. Obviously, once you do your routing, you can inform the customer on what delivery time you'll arrive there. Let's do an example. Now let's apply these guidelines for multiple vehicle routing to a real life problem. Okay. The triangle shows our warehouse. So right in Lansing, we have a warehouse and we deliver caskets. This is in Michigan, example from Michigan. The dots are funeral homes and they need the caskets. Okay. And the numbers are the weekly demand. So some funeral homes have one funeral a week. Some of them have 2 funerals a week. Some of them in near Detroit have 5 because as population density is more, 4, and so on. Okay. So you can see the demand. Okay. And we have to do our multiple vehicle routing because one vehicle can't carry all the caskets to hit all the customers. Also not possible to hit all these customers in one day. So we're going to have to do multiple vehicles and do a multiple vehicle routing analysis. Now, if you are doing, let's say, 5 deliveries in a week and one vehicle, the same vehicle does a delivery on Monday and then on Tuesday, then Wednesday, that's like multiple vehicle routing problem, because even if it's the same vehicle going on different days of the week, it's kind of like sending multiple vehicles out. You can't do, TSP just gives you one route. So if you were to do traveling salesman problem, you would just get one route with one truck hitting all these customers and coming back. You don't want that. Okay, you might have one truck going to one region on one day of the week, because this is demand per week. So let's say the funeral home near Flint needs 2 caskets a week. You just hit them on Monday. You don't hit them again till next Monday, right? So this is demand per week. So if you hit them on one day of the week, you can then deliver to other customers on other days of the week. So even if you have one truck doing like 5 different routes on 5 days of the week, that's a multiple vehicle routing problem, even though physically the vehicle is one, because you're going to come up with 5 routes. TSP only gives you one route. So the multi-vehicle is really multi-route. You're going to get multi-routes. It's not necessarily that physically you'll have multiple trucks. Okay. So we'll see, we can use one truck if we can do this in 5 trips in a week. If we can't, then we'll use multiple trucks. So when you do the routing, that's really when you'll discover exactly how many trucks you need as well. Okay, so let's do this case study. How do we build these routes? Remember, step 1 here, do clustering. We have to group customers together which are close to each other. And a cluster, when we do clustering, we have to make sure that the demand in each cluster can be satisfied with approximately one truck, because each cluster is going to get one route. And we want one truck to do one route. And a cluster should not be so large that you have to send 2 trucks to a cluster, and a cluster should not be so small that you just send a half-empty truck to a cluster. So very small clusters are bad, very huge clusters are bad. The cluster size kind of is going to be based on the truck capacity. So this is one option. So we pick all the customers close to Lansing as one cluster, and then the far away customers, we split them into 4 regions, like Northeast, Southeast, Southwest, and Northwest. Okay, these 4 regions. And that gives us 5 clusters. And if we can get it done with 5 clusters, that's going to be awesome, because we can just have one truck do one cluster a day, because they do delivery once a week. Notice what happened to Detroit. We split the region around Detroit into 2 clusters. And you might wonder, why is that? The customers in Detroit, there's a big cluster of customers. Why not just hit all of Detroit in one day? The problem is because there's so much demand in Detroit, okay, that if we were to make a cluster that captures all of Detroit, it's going to be very hard for one truck to carry all those caskets and to hit all of that in one day. So sometimes if you have a very concentrated demand point and you can't do all of that demand area in one truck, then you may split it into two clusters, half in one cluster, half in another cluster. Okay. What this also allows you to do, if you had Detroit all as one cluster, that'll be a small cluster, then your other cluster will be really large and the truck would have to travel very far distances in the other clusters because you have a tiny cluster, so all the other space is going to go into three clusters. And then that could really have the truck have trouble completing the other customers, and you may have to go for a second truck. So we're going to try this way. This is not guaranteed to be optimal. We're going to try this way. If it works out with these 5 clusters, our delivery works out, then we'll stick with that. Otherwise, you could try, putting the whole of Detroit into one, the large demand area on Detroit to be one cluster. So you can try both ways. This is how we're going to try initially. Okay, so we make these 5 clusters, and so we have tried to make them geographically approximately equal. Obviously, some are bigger because they're more spread out. So they're not all the same size, but approximately the same size. And we've tried to make sure the demand in each cluster is approximately equal. It's not going to be exactly equal, but we've tried to make sure that it's not that one cluster is very high demand and the others are very low demand. Here you can see we're building the routes, and because of the truck capacity and carrying the number of caskets and being limited to 11 hours, we do get 2 routes per cluster. Okay, our teardrop patterns are generally not overlapping. They are a little bit in this cluster here, so maybe we can improve this clustering a little bit. But for the most part, they're not overlapping, and they are for the most part teardrop patterns. So this would be a reasonably good solution. And this solution now tells us we need 2 trucks because each day of the week, 2 trucks need to go out to do a cluster. Okay. If we were able to do each cluster with 1 truck, then you can just use 1 truck and 1 cluster will be done on Monday, 1 on Tuesday, and so on. But even when we made 5 cluster, the demand in each cluster is more than 1 truck, and the time taken for all the deliveries will be more than 1 truck can do. And so we're using 2 trucks. So now, after doing all this routing, we know how many trucks we need. We need 2 trucks because we have to hit every customer once a week. We have 5 clusters. So we have to do each cluster one day of the week: Monday, Tuesday, Wednesday, Thursday, Friday. And because each cluster needs 2 trucks, we'll have 2 trucks. They'll do 1 cluster on Monday. The same 2 trucks will do the other cluster on Tuesday. The same 2 trucks will do the cluster on Wednesday. This is all done by hand on a map. So you can see without any complex software, it's a pretty complicated problem. Just by clustering and then drawing those teardrop patterns by hand, you can get to a reasonably good solution. A software may improve it 5%, 6%, but you're in the ballpark. You're in the ballpark of a good solution just with map and pen and paper. Okay? So don't be intimidated by routing. You can do it just without any technology. But if you wanted to, you could also do this using the Excel VRP software that I'll show you in the next video. Another heuristic method for the multi-vehicle routing problem, or the TSP, you can solve both problems with that, is called the sweep method. Okay, and you're going to learn very quickly why it's called sweep. Okay, so the best way to learn is from an example. So let's look at this example. A trucking company has 10,000 unit vans, so they can carry 10,000 units or whatever we are picking up. That's just the capacity expressed. Okay, you can express capacity as kilograms, cubic feet, and then just to compare when you're picking up stuff when you're full. Okay, for merchandise pickup to be consolidated into larger load for moving over long distances. So this could be a 3PL LTL company for LTL shipping. They collect loads and then they consolidate them and then move them over large distances. Or it could be a company that collects product from small suppliers or picks up stuff from customers and then it's shipped as could be customer returns, things like that. A day's pickups are shown in the figure below, which will be on the next slide. How should the routes be designed for minimum total travel distance? Now we are going to use the sweep heuristic here, and the sweep heuristic is pretty simple. So you plot everything on a map. So here's a map. You have a depot, which is the square. You have circles, which are pickup points. If they're delivery points, the system works the exact same way. So whether they're delivery points or pickup points doesn't really matter. Okay, and what we do with the sweep method is that we draw a line that we sweep in a clockwise. You draw a line from your depot, and then you sweep the line, which means turn the line clockwise or counterclockwise, whichever points you hit in which order, you add them up. And when you have hit the truck capacity, you come back to the depot and you start a new run. Okay, so this is the solution when I'm doing a sweep by 12 o'clock line. So I go from the depot vertically upwards, 12 o'clock position, and I sweep counterclockwise. Now there's no rule that you have to start at the 12 o'clock position. You could start at 3 o'clock position. You could start at 6 o'clock position. You could sweep clockwise. You could sweep counterclockwise. There's so many variations. I expect you to follow this because if I give you a question on a homework or an exam and I need to grade it, I need to know where your line started and which direction it went. And so because I just like to do 12 o'clock and counterclockwise, that's what you would do. Okay, but for this course, but in real life, doesn't matter really where you start. I mean, you'll get different solutions and you can compare them with different starts, but the method itself has no built-in preference. There's no logical reason to start at one direction versus the other. Now, the sweep method works when your points are around you in like a donut shape. So you can see that our customer pickup points are all around the depot in like a circle. And so the sweep method would work well. The circle doesn't have to be completely full. You could have points to the right of the depot and the left of the depot. But the point is with this method is that you don't have points right close by to the depot. Like the points exist like in a circle around the depot or in groups around the depot on the right and left, maybe top and bottom. And then you can just sweep to make clusters of them. And you don't have to worry about having some points very close to the depot where you have to come back and go back again. If you did have points really close to the depot as well as really far away, then you would want to handle the close by points separately because you don't want to be going far, then coming close, then going far, then coming close, then going far, then coming close over and over to hit some points close and some points far. Okay, so the sweep method, when I started at 12 o'clock position, I sweep left. The first customer hit is 4,000. Then I hit a customer for 1,000 units, 3,000. So I'm at 8,000. Then I hit a 2,000 unit customer here. I'm up to 10,000. My truck capacity, my truck has to return. Then after returning, I start my second sweep. Now it's kind of hard to see. You'll have to do it with a ruler on a paper whether the 1,000 point or the 2,000 point comes first. But whichever point comes first, these two will be on the same route. So let's say the 1,000 point comes first, and the 2,000 point, the next 2,000, that's 5,000, another 2,000, 7,000, another 2,000, 9,000. Now I still have 1,000 capacity left, but I have to return to the depot because the next point is 3,000 and I can't get the next point. So I return to the depot, then I go back out 3,000, 2,000, 3,000, and I come back. So I get 3 routes and the number of units picked up on each route is given, 10,000 on route 1, 9,000 route 2, 8,000 on route 3. So it's a really easy method and it's just clustering by angle based on the angle. So the customers which are close by in angle from the depot get clustered into one route. It does not factor in how far you are from the depot, which is why I said it works okay if all the points are relatively equidistant from the depot, or at least they're all far or all close. You don't have like 1 point far and 1 point close and 1 point far and 1 point close, because then you're going back and forth a lot. Okay, so that's the sweep method. Now, the last method we're going to do is called the clock right savings method. And this is perhaps of all the heuristics we have done today, the nearest neighbor, the sweep method, this is perhaps a little bit more complicated of those, but it can still be done by hand. Okay. And then the teardrop pattern method is also a heuristic you do by hand, right? So we did like these 3 heuristics, nearest neighbor, then we doing the teardrop patterns by hand after clustering by hand, then we did the sweep method. And then we're going to do this one, and this can be done in Excel or by hand as well, clock right savings method. And then the 4th one, which we talked about, which was the genetic algorithms, that we'll do in Excel in using the Excel VRP solver, which is a separate video. Okay, so clock right savings method, the logic is really straightforward, and once you understand the logic, all the steps will make sense. If you don't understand the logic, you'll be like, there's so many rules, there's so many steps, it doesn't make sense to me, how do I remember them? So forget the details at first, just understand the logic, which I'm going to explain in a few slides, and then we'll get into the details. So it's really important to understand the logic behind this method. It's a pretty powerful method, relatively still simple. You can do it by hand or in Excel, and gives you decent roots. So why do we want to learn the clock rate savings method? First of all, it's robust. It generates a good solution, a good to great solution almost always. Okay, it's often used to generate a starting point solution even by more advanced heuristics. Because remember I mentioned all these heuristics, they take a starting point solution and improve it iteratively. So this is a good way to generate a starting point solution for those heuristics or just to use yourself. It's simple, can be done by hand or in Excel, outperforms nearest neighbor sweep and eyeball solution, especially as the number of stops grows. Okay. Often can save small to medium-sized companies from having to purchase expensive routing solutions because it's often good enough. Okay, so it's really important. It's like a really good skill you can learn in this lecture on how to do clock rate savings method. It can handle multiple vehicles, multi-vehicle routing, and it can do TSP as well. And so it's really, really powerful. So here is the logic of this method. The logic of this method is I need to move towards a good solution. Okay. I don't know a good solution. But what I do know, I know the worst possible solution. So what I'm going to do is, I don't know where the good solution is, but if I move away from the worst possible solution, I'm going to end up at a good solution. Because the further away from you are from the worst possible solution, the better your solution is. So that's what you're going to do. We're going to start with the absolute worst solution, and then we're going to try to jump as far away from it as possible and keep jumping far away by adding what are called savings. So that's the key logic. Now, what is the worst possible solution? The worst possible solution in routing is to go to a customer and come back after visiting just one customer. So let's say you have customers A and B. You go to customer A and you come back. Then you go to customer B and you come back. There's no way to do worse than that. Okay? Because you're just doing one customer per trip. That's going to give you the longest possible routing solution. As you combine customers on trips, you save money, time, distance, and you do better. Okay. So savings are defined as what is the distance saved if you take 2 points that you're visiting individually, points A and B. You visit one, you go back, you visit the other, you go back. And instead of visiting them individually, you combine points A and B on one route. So that's the two pictures. The first picture on the left shows you go to point A, you return. You go to point B, you return. The total distance traveled in this first diagram is going to be D0A, where 0 is the depot, and 0, A means you're going from depot to A, the distance between depot and A. That's D0A. That's going to point A right here. Then coming back is going to be DA0. Okay, and we are going to work with the simplifying assumption that D0A and DA0 are the same distance. So the distance you travel to go to point A from the depot is the same distance on the way back. And usually that's true. Almost always that's true. There's sometimes there could be like a one-way shortcut. You can take one way but not the other way, right? And there could be issues like that in rare cases. But for the most part, going to a point and then coming back is the same distance. Okay, so we do go D0A plus DA0. Then we go D0B, which is the distance to B. Then we come back from point B, which is DB0. So if I add up these four terms, I get the distance of my initial solution, which is terrible, because I'm visiting each customer individually. Okay. Now this simplifies to 2 times D0A plus 2 times D0B, because DA0 is just D0A. They're both equal. Okay. Going to A and coming back from A is the same distance. Now, what happens if I combine A and B on the same route? So I go from 0 to A, D0A, then I go from A to B, DAB, then I come back D0B. So my distance in this combination becomes D0A plus DAB plus DB0. And remember, DB0 is the same as D0B. So how much distance have I saved by combining points A and B on the same route? Well, we compare the initial distance, which is 2 times d0a plus 2 times d0b, because db0 is just d0b, so these two add to 2 times d0b. This initial distance, you subtract from it this distance, which is the combined route distance, d0a plus dab plus db0. Okay, d0a and d0a subtract out to a 0. So you have just one dA0, which is d0a. The d0a is left, which comes here. And the db0 and the db0 subtract out because db0 minus db0 is 0. And the remaining d0b comes here. And then you get a minus dab because this whole thing is being subtracted from that initial thing. So each of these has a minus sign now because they're being subtracted. So you get the savings by combining points A and B is distance between depot and A plus distance between depot and B minus distance between A and B. Okay? So that's your savings. And we're going to calculate the savings for all possible pair of points. And then we're going to start building routes by picking the highest savings. The 2 points that save us the most by being on the same route, we start building our routes from that because they give us the furthest jump away from the worst possible solution. Then you add the next highest savings, you get another jump away from the worst possible solution. Each time you incorporate savings into your routing, you're jumping away and away from the worst possible solution, i.e. towards a good solution. So that is the logic. The points that offer the greatest savings when combined on the same route are those that are furthest from the depot and that are closest to each other. Because you want D0A and D0B to be large, so they're far from the depot, and you want DAB to be small, they're close to each other. That's why the savings is the highest. Can the savings be 0? Yes, if 2 points are on opposite sides. So if here's the depot, and point A is here, and point B is here. Then whether you do individual trips like this, so you do 2 individual trips, or you do 1 trip, or you go here, and come back as 1 trip. The 1 trip and the 2 trips, they have the same distance traveled because the points are exactly opposite to the depot. And in this case, the savings will be 0. SAB will equal 0. You save nothing by combining them onto a route. Okay. Can the savings be negative? Well, let's say this is the depot. This is point A, point B. When you combine them on a route, you get a triangle. Okay, this is a triangle. So by the triangle inequality, D0A, which is this side, plus D0B, which is the second side, when you add these two sides of a triangle, that must be bigger than DAB. Okay, which means the savings cannot be negative by the triangle inequality. But this is assuming you live on a flat plane, and we know the Earth is not flat. So if very large distances are involved, which is unrealistic, unlikely, when the Earth's curvature comes into play, and then you have roads which are not going in straight lines, and it's possible that there's a mountain here, right? And then this will have to curve up and down the mountain, making DAB very large artificially. So mountains, curvy roads, Earth's curvature, all these things can throw the triangle inequality away. And so in real life, you can get a negative savings. Okay, it's going to be rarer than rare because it have to be over large distances usually, or some really like weird, like a lake in the middle of 2 points, and you have to go around the lake, things like that. Okay, it's going to be very rare. Okay. But it doesn't matter whether the savings are 0 or negative, the algorithm still works. It just deprioritizes those savings, and you don't combine those stops on the same routes usually, so to avoid the truck having to go around the lake or over the mountains and so forth. And so the algorithm still works. Whether savings are positive or negative, it will prioritize the positive savings, move the negative down the list. But yes, they can be 0. Very, very rarely, not on a two-dimensional plane, but in real life, with all these, when you have distances based on roads, not straight lines, they can be negative. So here's the algorithm. And if this slide doesn't make sense do not worry. We're going to run through an example. The example will clarify what you do. And then this is kind of like for your reference. Once you do the example, you'll understand what these steps are talking about. Then you can come back and read that. It'll make more sense. So I'm just going to read it through quickly and then focus more on the example. But this slide will make a whole lot more sense once you've done the example. So step 1, we calculate the savings for every possible pair of locations, which is your customer points or pickup points or drop-off points, Sij, which is point I, point J. When they're combined, you get savings S. And the savings formula is Sij equals distance between depot and point I plus distance between depot and point J. Depot is just your starting point, your factory. It doesn't have to be a warehouse. Could be a factory, could be a port, whatever your starting and ending point is. So D0J minus distance between I and J, where O is the origin, which is the depot, warehouse, factory, whatever your starting point is. Then we rank the savings in descending order of magnitude. Actually, in descending order, because if you have negative savings, they go down, they can't go up, to create the savings list. Okay, so we rank the savings in descending order. And then we go through the saving list in order and include link ij in a route if no route constraints are violated and if one of the following holds. So what are route constraints? Route constraints are things like truck capacity. So if your truck is full, you can't add another link to that route. The truck has to come back, start a new route. Okay. Now, if you get a link ij, which is savings of ij, those at the highest savings, it picks two, you pick that saving that identifies the 2 points the savings is between. You want to add those points on a route. If neither of those 2 points have been assigned to a route, you start a new route with those 2 points. If exactly one of the 2 points has already been included in an existing route and it is one of the boundary points on the route, you can attach this link to that boundary point, kind of like Lego attaches at the ends, but not in the middle. So if you have a route going, BCE, and then you get a savings of EA, you can add EA to the E at the end of the route. But if you get savings CA, you can't add A to C because C is in the middle of the route. You only add links to the 2 ends of the route, the start of the route or the end of the route, okay, for an existing route. And if both I and J have been included in 2 different existing routes and they are the boundary points, then those 2 routes can be merged into one, okay. But if none of that holds, then you just throw away the savings. You can't do anything with it and you go to the next savings. And you keep going until you have all the customers are part of routes, until the savings, okay. So if the saving, so you keep doing that until you have any customers left unvisited. If you exhaust the saving list and you still have points you have not visited, okay, then you will have to visit them individually because there's no saving to be had by combining them with other points. Okay, so slight correction. The last point should have said if there are still unvisited customers and the saving list has not been exhausted, then we return to step 3. Because if you have visited all the customers and you still have savings list left, you just stop. There's nothing else left to visit. You don't need to go on. Okay, so let's do this example. So we have 9 customers labeled points 2 to 10 because in this example, point 1 is the depot. Usually I try to label point 0 as the depot. And so point 1 is the first customer, but in this example, the notation is a little bit different. And so just bear with me. Point 1 is the depot and nodes 2 to 10 must be visited. They are the customers. So we are going to collect or deliver. It can be either way, it doesn't matter. Okay. So at each point, we may be delivering pallets or collecting pallets, doesn't matter, but that's the number of pallets quantity. And our truck can hold 23 pallets total. Okay. So if we have hit customers worth 23 pallets, we have to come back and then go again. So this is like a savings matrix here. So let's understand this table. So point 1 is the depot. On the lower triangle, okay, which is this part of the matrix that I'm in the blue triangle, these are distances between points. These have to be given to you in the question. Okay, this is distances ij, and they are given in the question. So the question tells you the distances between points. So you can see that node 2, which is the customer, is 25 miles from the depot, which is node 1. Okay, so D12 equals 25 miles. Okay. Do a self-check. What is the distance between points 5 and 6? So if you go to this row and this column, this 27 is the distance between node 6 and node 5. So D56 equals D65 equals 27 miles. Whether you go from A to B or B to A, it's the same distance in our, because that's our assumption, right? We say that going from one direction, going the other direction between the same 2 points is the same distance. That's our simplifying assumption. Okay? So that's how you can find the distance between any 2 points in the lower matrix. And that's why you only have the lower matrix, because the distance is symmetric. D56 equals D65. So we actually find D65, which is 27. So D56 equals D65 is 27 miles. This, for example, here is the distance between node 10 and node 3. So D310 equals D103 equals 114 miles. Okay, so that's how we read the distances. Once we read the distances, okay, let me clear some of the mess I made. Once we read these distances, we can now calculate savings, because savings are just based on the distances. Okay, so let's use our savings formula to do a couple of examples. Okay, let's pick 2 points and verify what the savings are. Okay, so let's verify this savings of 0. So what it's saying here is that the saving between 0.7 and 0.3, saying S37 equals 0. Let's verify that. So S37 by definition is distance between depot and node 3 plus distance between depot and node 7 minus distance between 3 and 7. So what is D13? D13 is 43 right here. D17 is 29. Now we need D37, so we go to the 7th row and the 3rd column, that is D73 or D37, which is 72. Okay. Now 43 plus 20 gives us 63, and then plus 9 43 and 29. 40 and 20 give us 60. Then we get 63, then plus 9 gives us 72. And then minus 72 gives us 0. So this is 72 minus 72, which is 0. Let's verify this huge savings of 77, which is saving S65. So S56, okay, it's going to be depot to 5, D15. Notice depot is often 0. So this could be D05, but in this example, depot is 1. So this is your depot in this example, or the warehouse or the starting point. I'm just calling it the depot, but it could be the warehouse, the starting point, the port, the factory, whatever it is where your truck starts from and has to return to. Plus D16 minus minus D56. Okay, so D15 is this, which is 43. D16 is this, which is 61. Minus D56 is D65, which is 27. Okay. So 40 and 60 give us 100, plus 3 and plus 1 is 104. So it's 104 minus 27. So if I do 104 minus 20, I get 84. And then when I subtract 7 from 84, I get 77. So I get the savings. So notice you just calculate saving between all possible pairs and just put them in this matrix, or you can just write them down in a list and then you can just sort the list. That's fine too. And notice, why is there no savings? Why is there no S12 here and S13 here? Because you can't, one is a starting point, you have only one customer. By definition, you can't have savings between the depot and a customer. You have to combine two customers on a route to get savings. So S12 does not exist by definition. Does not exist because it's not possible. You need two customers to have savings, and you just have one customer too. One is not a customer, one is a depot. Yeah. So this row will be this row will be blank. Okay. So here are all of our savings in this triangle. The reason I like using a triangle like this matrix to fill savings is I know when I'm done, I've done all the savings. Because otherwise you have to be careful. You have to make sure you calculate all possible savings pairs. And this by doing it in a matrix like this, I know when the matrix is full, except with the top row, then I'm done with calculating my savings. Okay. If I'm giving this a question like this on the exam, either I'll just ask you to calculate certain savings and not do the whole process, or I'll give you a matrix like this with all the savings and then you'll have to make the roots. So I'll not ask you to do the whole thing from scratch because it can take a little bit of a while. Yes, those are examples of savings calculation. Now that when you have the savings in this matrix, you have to sort them. So the biggest saving is 86, I believe. Yep. So you write that first. This is going to be S610. See, S610, this is savings on 610 is 86. Then the next biggest saving is 83, which is S910. Okay, this is S910, savings 910, which is 83. So just write them as a list, and then the list continues here, and then continues here, right? So we just write them as a list. And now we're going to start building roots. So basically the first savings is S610. S610. Okay. Now, if you go back to your rules, 0.6 and 10 are on no root at all. There's no existing roots. So we don't have 0.6 and 10 on a root. So our roots will start a new root, root 1. And I'll put 0.6 and 10 on it, customer 6 and 10. And I've used up this saving, so I can kind of knock it off the list. This is done. Because you can't reuse a saving again. Because you don't want to visit a customer twice. Then I pick the next savings, S910. Now, in S910, 10 is already part of a root. So it's not this situation here where none of them are on a root. Exactly one of the 2 points is in a root. Because 9 is not in a root and 10 is. Okay. So it's this case right here. Exactly one of the 2 points is on a root. Now, because 10 is an end point, it's not in the middle because end points of a root are the two extreme points. So this is an end point of my root 6, and 10 is also an end point because my root is just two points long. So 6 is an end point. I can add stuff here, and 10 is an end point. I can add stuff here. So what I'll do is I will take 9 and I'll add it here. This will become 9. And when you do 10 and 9 like this, you're incorporating the savings right here. S910 is the same as S109. Remember? So S910 or S109 is the same thing. So when I do 10 to 9, S109, I've incorporated S910. Okay? So that's done. So this is also done. Okay. Oh, one thing I have to check is my load on this route. So if you look at the customer demand, okay, customer 6 needs 27, 10 needs 4, so that was 11, and then 9 needs 4, that's 15. So I'm at 15 on my truck. I still have capacity. My truck capacity is 23, remember? Okay, so I can go on. So 8, 9 is next. Okay, so 9 is already the end point of route, so I can just add 8 here. And I've used up this savings, and let's look at customer 8. Customer 8 has 5 units, so my truck usage goes up to 20 because I have to carry 5 pieces for customer 8. Okay. Now look at 5, 6. I can add 5 to the left of 6. Let's just check the capacity. Customer 5 needs 4 units. So I cannot add customer 5 right here. Okay, because this would take this up to 24, which would exceed the truck capacity of 23. By the rules here, I can add 5 to the 6 because 6 is an endpoint, and I can attach 5 to an endpoint. But I exceed truck capacity, so I can't do that. Okay, so we can't add 5 to 6. So our route 1 is kind of done. Okay, this is our route 1, 6, 9, 10. So now S5, 6 cannot be, 5 can't be joined here. And I can't start a new route with 5, 6. Imagine if I did this. A new route based on this saving. Well, that's problematic because now 6 is visiting by truck 1 and by truck 2. I have 2 trucks going to the same customer. That's not right. So I can't even do that. So I just have to leave this savings and move to the next one. 8, 10. 8 has already been done, 10 has already been done. See, 8 is visited, 10 is visited. So if customers have already been visited, don't visit them again. 7, 10. So 10 is an interior point. You can't add 7 here like this. You can only add to the exterior points, the boundaries of the route on the right and left. You can't add to the middle points. So we ignore that for now. So we just ignore this for now, ignore this for now. Then we get 4, 5. Both points are unvisited. Okay. So we create a new route. 4, 5. And the truck on this route is going to have customer 5 has 4 and 4 has 5, that's 9. So this has 9 pallets for now. Okay. Okay. So we use this up. Now we have 6, 7. 6 has been visited. 7 has not been visited. So we could add 7 to the other side of 6. It depends on how much units does customer 7 need because we have only capacity of 3 there. Customer 7 needs 3 units. Wow, that is perfect. So I can add 7 here. And my truck usage would go up to 23. Full truck. Now I can't add anything to route 1 because that's a full truck. So I've used this up. Now we have 5, 10. 10 has already been visited. 5 has already been visited, even though they're on different routes. And we can't even connect these 2 routes because 10 is an interior point. Do you see? I can only connect at 8 or 7. So I can't even connect 5 to 10 to make it one route. Also, it's out of capacity. There's multiple reasons you can't connect them. And both customers have been visited, so do nothing. 3, 4. I can add 3 here. Most likely I have enough capacity. Let's check capacity. Customer 3 wants 6. I have 6 space. 9 plus 6 is 15. So this goes to 15. Okay. Now I have 1, 2, 3, 1, 2, 3, 4, 5. So I have 8 customers visited out of 9. I have just customer 2 left. So I'm almost done. Okay. So I did the 3, 4. Now I get 2, 4. I can't add 2 to the 4 because 4 is in the middle. So I just have to ignore this. Okay. I get 6, 9. They've both been visited. 4, 6. They've both been visited. 7 and 9 have both been visited. 7 and 8 have both been visited. Plus that route has no capacity. 2 and 3. Oh, I can add 2 to the 3 here. Okay, if I have enough capacity. So customer 2 wants units 4. I can do that. So that will become 19 because I added customer 2. Okay, so here are my routes. Now when you are done, you can add depot on both ends. So I'll do depot, I'll call it D. So route 1 becomes D to 7 to 6 to 10 to 9 to 8 and back to D. Okay, and route 2 becomes depot to 2 to 3 to 4 to 5 and back to D. And you can go in either way. You can go clockwise and anti-clockwise. It's the same route. Whether I go D7, 6, 10, 9, 8 back to depot, or I go the other way. Depot 8, then 9, then 10, then 6, then 7 back to depot. So I go left or right, it's the same route. It's like a circle and you can go this way or that way. You get the same distance total. So these are my 2 routes. Route 1 will have a full truckload of 23. Route 2 will have a truckload of 19. So that's how you build route, by going down the list of savings once you have it in descending order. Okay. So these slides just explain all of that. So we start with 610, and then everything I explained, you're just going to list it on these slides. Okay. And you'll see that we end up with the same solution that I just arrived at with you. So we can just stop when all points have been visited. So this is our final answer with the clock right savings method. Okay. So that's it for this topic. Just to recap, we did the traveling salesman problem, the multiple vehicle routing problem, we looked at nearest neighbor, we talked about genetic algorithms or two option swap heuristics, but we'll do them in Excel in a later lecture, Excel VRP template that I'll give you. And then we looked at the sweep method and the clock right savings method as other heuristics that we can use. We also looked at manually doing it by doing clustering and then doing teardrop patterns manually, which we said works really well as well. So you have all these tools to attack this sort of problems and do routing in real life. Especially once you watch the next lecture, which uses Excel VRP. VRP is vehicle routing problem. Use the Excel template, which has a genetic algorithm built in to solve this for you. You'll have a bunch of powerful tools at your hand to do routing should you need to.